Hello and welcome to the first lecture of Bio 111, Unity of Life. So today's lecture will be about the molecules of life, part one. There will be a second part for the next lecture. So let's start by looking at tissues, cells, organelles, atoms in a hierarchical order in biological systems. So when we talk about systems in biology, there are, of course, organisms, for example, in animals. So there's the entire organism. You can talk about organismal biology. And then there are organ systems, so parts of the organism that are working together. For example, the circulatory or the excretion systems. Then there are certain tissues, types of tissues that together make up the organ system. And then there are cells within the tissues. And then these cells contain organelles. Those are little parts of the cell, and we will talk about those in more detail later on. And then, of course, these organelles, again, are made up of molecules, such as proteins, DNA, fat, and sugars. And then these molecules are made up of atoms, which are, for example, carbon atoms, or hydrogen atoms, or sulfur atoms, other kinds of atoms. So we will talk about this hierarchical order, but today we're going to start to just look at the very smallest level of all of this, the atoms and the molecules that make up biological systems. You will learn some of this also in chemistry, and so there will be sort of a back and forth between chemistry and biology, but we will spend a little bit of time in this first lecture to discuss what atoms are, what molecules are, what they're made of themselves. So in this figure from your book, you'll see that a atom, in this case it's the carbon atom, that it's made up of a nucleus, and the nucleus itself is made up of protons and neutrons, and they have the different shadings here. And then they are surrounded by electrons, and these electrons are shown here by these uncertain places where this electron might be at a given time, because the electrons sort of swirl around the nucleus, just sort of like planets that circulate around a star. So by definition, an atom is the smallest unit of matter of a particular element. And an example of an atom would be one atom of sulfur or one atom of carbon. And then atoms themselves consist of neutrons, protons, and electrons. Now, what is an element? So here's another definition that we need to discuss. An element is defined like this: a substance that cannot be broken down to other substances by chemical reactions is called an element. So, for example, any amount of carbon. So it doesn't matter how much you have, how many molecules, any amount of carbon would be the element of carbon, like a little pile of carbon. Then we have compounds and we have molecules. Compounds are substances that consist of two or more elements. So we talked about elements before, for example, carbon and hydrogen. But together, put together, a compound would be a substance that has two or more elements. So in this case, the example is methane, CH4. Now, a molecule and a compound, that can be a little tricky to distinguish. A molecule consists of two or more atoms, but doesn't have to consist of more than one element. So what that means is that, for example, methane, that is a compound, is also a molecule because it consists of two or more atoms. In fact, it consists of 5. Hydrogen, which always occurs as a molecule, as a substance that is made up of 2 atoms, is also a molecule. So H2 is also a molecule. O2, oxygen, also always occurs in the molecular form with O2. Okay, so now that we have those kinds of terms defined, let's look at how an atom is made up. What does an atom look like? So your book has some figures, and I would urge you to take a look at those more closely. But I want to go through some of these figures with you and just sort of see what we can get out of those. So I said earlier on that electrons swirl around the nucleus, and electrons are negatively charged and the nucleus is positively charged. So there is some sort of a attraction because of the charge difference. But there's also the reason that electrons can maintain a distance from the nucleus is because they have a certain speed, they have a certain amount of energy that allows them to swirl around and not collapse into the nucleus. Now the question is, where are these electrons? And these electrons, depending on how many electrons an atom has, they will be in certain places, let's say, where it's most likely that an electron will be found. So, in fact, I can already tell you the area within an atom or molecule where electrons are found more than 90% of the time are called orbitals. And depending on their energy content, electrons occupy different orbitals. So, more or less energy in that particular electron in a given space, different orbital where it might be. So let's look at what these orbitals are, what they look like, and how we draw them so we can better understand them. So if you have hydrogen, hydrogen only has one single electron. That's it. All it has is one electron, and that is in one orbital, and that's the single orbital that is closest to the nucleus. Now, if you have more electrons, and I'll show you a number of compounds or elements really that have different numbers of electrons in just a bit, they will then fill up the other orbitals that are available to these electrons in these atoms. So other types of orbitals that are available that potentially this electron can occupy are yet another spherical orbital, but then also these dumbbell-shaped orbitals, or these figure-8-shaped orbitals. So this electron can, in this kind of orbital, swirl around in circles like this, can also sort of crisscross. Less likely to crisscross through the nucleus, of course, because that's positively charged. But if they are occupying one of these dumbbell-shaped orbitals, then they sort of go around in a figure 8. Again, avoiding the very nucleus. So all of that together gives a picture of the orbital space where the different types of electrons may be at a given time in their locations. So these are orbitals. Now, the orbitals can also be drawn in a different way, and so your book calls it a simplified diagram, in which you can also imagine these electrons to be. So again, if we looked at the first orbital with the hydrogen as an example, then we could draw it like this, but we can also draw it like this, just like a planet around a sun, where this electron is the planet, and it describes this particular way of moving around the nucleus. And you can see there's only one orbital, there's only one electron, so this has to be hydrogen. Carbon has 6 electrons, and they are assorted like this. So the first one, the first orbital, the smallest one in the middle, that's the same orbital as hydrogen has, well, that can actually hold 2 electrons, but no more. And so you can see that in carbon, those that is completely filled up with those 2 electrons. And then there's a second orbital, and that orbital can hold 4 electrons, and that is also completely filled here. So these electron energy levels are depicted as circles, and the electrons that occupy them as dots. And the cloud in the center is the nucleus. So these are also called shells. Now, I say here, these are found more than 90% of the time in these places that we call orbitals. Well, where are the other 10% of the time, right? So electrons are really not static. They move around quickly. And so they can also sometimes leave this space that we as scientists assign them to. Of course, they don't know any of the fact that we have assigned them this particular space. And so the fact that the space is called an orbital, and that we even have a place where we assume the electron will be most of the time, is all proportional to where in fact they can be measured. And so they are jittery, they go around somewhat randomly, but not so randomly that we couldn't say more than 90% of the time they will be found most likely in this particular place. So that's why there's this sort of uncertainty in the number. Okay, so we talked about orbitals, we talked about shells, we talked about electrons and where these electrons are found around the nucleus. Now let's take a look at how we can sort this a little bit better so that you don't have to guess how many electrons a certain atom might have. And for that, we have the periodic table, which sorts the elements by their number of protons. So it could also sort them by the number of electrons or neutrons, but it is sorted by the number of protons. And so this is one way of depicting this periodic chart or periodic table. And in different depictions of the periodic chart, there are different pieces of information that you can get out of the chart. All of them will give you the names of the elements, and they all have them sorted in rows and in columns. So you'll see that there are spaces that are left out. For example, here in this first period, there are only two elements, hydrogen and helium. And they have 1 proton for hydrogen and 2 protons for helium. And if you look at any of the other ones here, vanadium, for example, 23 protons. Selenium, 34 protons. So you can see that they are sorted with ascending order of the number of protons. This also shows you now in shading the abundance of this particular element in cells, in living tissues. So you can see there's tons of carbon, nitrogen, oxygen, phosphorus, and hydrogen. And then there's quite a bit, but much less sulfur and chlorine, or mostly as chloride. Sodium, magnesium, calcium, and potassium. And then there are the traces. Those are the kinds of minerals that humans or plants or animals need. And then they're the ones that are usually not found in living organisms. So we'll come back to periodic tables, but I wanted to show you how you can sort the elements. Now, there are a number of things about each element that one can know and that you can, in some cases, find in a periodic chart. So first of all, we have the atomic number. That is the number of protons, which I already alluded to. And when you write that out, if you wanted to say, if you wanted to determine in writing what the number of the atomic number was, then you write that as a subscript in the left lower corner of the letter symbol for this particular element. So in an atom, this will never vary for the same element. So helium always has the atomic number 2. Now the mass number, which you see up here in the upper left-hand corner, not the lower left-hand corner, is the sum of all protons plus neutrons in an atom. And that can actually vary a little bit. So in most cases, for each proton, there's 1 neutron, but that's not always the case. And so where that is not the case, we have what's called isotopes. So each form of an element with a different number of neutrons, but the same number of protons, is called an isotope of each other, if you will. So for example, we have here 3 isotopes of carbon. They're all the same element. They all have the same atomic number, which is 6. They all have the same mass number, the same number of protons. They have the same number of protons, not the mass number. The mass number that you then see up here in the upper left-hand corner, 12, 13, or 14. And that is because they have different number of neutrons. You see this one has 6 neutrons, this isotope has 7, and this one has 8. And if you add 6 and 6 together, that's the mass number 12 here. 7 plus 6 is 13. That's the number up here. And then 14 for 8 neutrons and 6 protons. And so many different elements have these slight variations. And so they exist in multiple forms, and those forms are called isotopes. So carbon commonly has 3 different isotopes, although the most common of these isotopes is the 12-6 isotope form. 99% of carbon exists in this form. Now, you might have heard that term isotope before, and you may associate it with radioactivity, and that's because people often talk about radioactive isotopes. Isotopes just means that they have that they're the same element, but they have different number of neutrons. But some of these isotopes are unstable. That means they're just not stable enough that they can just sort of form a nucleus that will always stay together. They decay over time. And so an element that decays because of its unstable nucleus is called a radioactive isotope. It's an unstable isotope which decays and gives off particles in that process and energy. And then we have the atomic weight, and the atomic weight is the sum of the protons plus the neutrons in an element. And when you see just one number in a periodic chart, you often see that that's a fraction of something. It's not just 13 or 14 or 12. It will give you a number, maybe 12.1 or something. And that is because that's an average of all the different isotopes that there are. And if there are multiple isotopes, then depending on how frequent they are overall, then that will make up or determine the overall atomic weight. Okay, so now we've learned quite a bit about the periodic chart already. Let's take another look here and try to combine those two things together. We looked at the periodic chart, we looked at these different elements, we looked at their shells, we looked at the electrons, and now what I wanted to point out to you again, I mentioned it earlier, is that the number of electrons changes across from the left to the right of the periodic chart. So helium and hydrogen are sort of a little bit different in their first period, but in the second period here, we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. And you can see in this depiction on the top here that the first shell is fully loaded with 2 electrons, and that's the same in all of these different elements. It's always 2 electrons right there. But the next shell, the outermost shell, which is also called the valence shell, I'll write that down on the next slide. The valence shell, you see how that starts with just 1 electron here, then 2 electrons, then 3 electrons, 4, 5, 6, 7, and 8. And at that point, the valence shell is full for the second period. One also says or refers to the valence shell being filled with electrons from the left to the right. So that is what makes up the difference between one element from the next element. How many electrons, of course also how many protons or neutrons. But as you fill in the electrons to counterbalance the protons in the nucleus, that gets done in a very orderly manner, or really, the way that we made the periodic chart is what gives it the order, right? We are producing the order in the natural way of how elements simply are. Okay, so talking about elements, let's just sort of take a look and see what kinds of chemical elements are found in living cells. Here's an example from your book for human cells. You see that the vast majority of the chemical elements found in human cells is carbon. 47% of all dry mass of the chemical elements is carbon. The next is oxygen, then hydrogen, nitrogen, phosphorus, sulfur, and here's all the others that I also pointed out by the shading in the periodic chart. Okay, so now we know what atoms are, what elements are, what atoms are made of, and how elements differ from each other in a chemical way. So knowing that is very important for us to understand how they react with each other, how they interact with each other, because it's the electrons really between different elements, between different shells that interact with each other and that produce compounds, that produce bonds between electrons that will then produce the various different types of compounds that make up life. So let's next spend a little bit of time to look at the types of bonds that are made between atoms to produce molecules and why they are made the way that they're made. So I mentioned the valence shell already, so that's the outermost shell, and the chemical behavior of an atom depends on the number of electrons in the outermost shell. And so these outermost shell electrons are also called the valence electrons. So take a look here. Methane has 4 hydrogens, and each of those hydrogens have 1 electron to contribute. Carbon itself has 4 electrons to contribute in its valence shell, in its outermost shell. And so together between carbon and hydrogen, you see 2 electrons sort of sharing the overlap here between carbon and hydrogen. And that is the same way over here and over here and over here. And if you consider that hydrogen has an electron to contribute to a bond with, let's say, carbon, and carbon has 4 total. So there's 4 from each of the 4 hydrogens, 4 electrons, 1 each, and 4 from the carbon that can come together to produce this outermost shell. And the outermost shell has 8, and 8 is the total. That's it. You can't add any more than 8 to this valence shell. Well, the reason why we know that is because because that is the way that we have the periodic chart set up. After that, when the periodic chart shows that there are more electrons that need to be distributed onto a certain element, then we start a new period here. We start a new row. So the way that your book shows this is that overlap between these shaded areas, there's always 2 electrons that are sharing this shaded area, and that is what you will see in a second makes up the bond. So nitrogen has 5 electrons in its outermost shell, oxygen has 6 electrons outermost shell, carbon has 4, and stability usually occurs when you have a total of 8 electrons in this outermost shell, regardless of whether it's your own by yourself or whether it's shared with other partners. And so if I say oxygen has 6 to add and hydrogen has 1 each, then this together will give you 6 plus 2 is 8. Nitrogen has 5, so it can pick up 3 electrons from 3 hydrogens. And so 3 electrons from 3 hydrogens, that's 3 plus 5 is 8. And here we have 4 plus 4 from carbon, that's also 8. And so this will give you stable valence shells. As I said, hydrogen is a little different, so is helium. They are already happy with just 2. But that's really the only ones in the entire periodic chart. Okay, so we are interested in all of these molecules because those are important molecules in life, water being chief among them. So let's take a look at water, and let's take a look at why electrons and the distribution of electrons within these shells or the orbitals. Those are really similar words, then they're just different ways of describing the same thing, right? Where are the electrons? So you can use one or the other. You don't have to worry about using both. So how are they distributed? So there are ways to show this, and you will see mostly this particular formula. You will see the structural formula and the chemical formula. So the chemical formula just gives you the letters and the numbers of each of the atoms that make up the molecule or the compound. The structural formula will tell you how they are arranged with respect to each other. Sometimes it tells you something about charges or partial charges. We'll come back to that in a little bit, but you already see these pluses and minuses and these deltas. Delta means partial charge as opposed to full real charge. We'll talk about the difference. But that you can also see in the structural formula. And then there's the space filling model. You often see that in chemistry, not so much, you won't see that so much in this course. It tells you a little bit about the size, how they are arranged. And then the molecular orbitals, will even less talk about those. So, but we will want to talk about the different types of bonds. And we will want to talk about those in quite a bit of detail, because there is a lot of structure-function relationship between the structure of the molecule and the reason why it has this structure and the function of the molecule in a biological system. So let's take a look at that. With respect to water, what I want to point out here is the first type of bond that we will learn about. We'll learn about 4, and that's the covalent bond. So covalent bond is made up of mutually shared valence electron between 2 or more atoms. So that is how a covalent bond is defined. Mutually shared valence electrons between two or more atoms. Two or more atoms right here. These are the two electrons that are depicted by a line, and they are shared between oxygen and hydrogen, just like you see here. Oxygen and hydrogen, these two electrons, that is what is referred to over here in this particular line. So those are the shared valence electrons. Okay, so covalent bonds, that's the first. Definitely something to write down, definitely something to remember. Very important to know how a covalent bond is made up and how it's different from the other types of bonds that we will discuss in a moment. So, second type of bond, that's the ionic bond. Also important to write down. So an ionic bond is created when atoms either completely give off their valence electrons or fill up their valence shells with electrons from another atom. Charged atoms created in this way are called ions. That's why it's called the ionic bond. Okay, let's unpack that a little bit. Let's see how that is different from the covalent bond. So your book shows you an example of a chlorine atom and a sodium atom. And you can see again the innermost shell, 2 electrons, that's all it can fit. You see the same is true for chlorine, innermost electron shell can only hold 2. The next one can hold up to 8, and you see that this is full, and so that's the same case here in sodium. Next shell is full with 8 electrons. But sodium has one more extra electron, and just to look quickly here at the periodic chart, sodium is right here, has 1 extra electron, whereas chlorine is all the way over here with 7 electrons. And 1, 2, 3, 4, 5, 6, 7. 7 electrons. So it's just missing 1 electron for it to have a stable outer shell. So if it could just find 1 extra electron from someone, then it would be really, really happy, or, not really happy, but it would be stable. And since sodium could achieve the same stability by giving off its extra electron, if it could only get rid of that 1 extra electron, it would be stable. So together they make a great pair, because now if sodium just completely transfers its electron to chlorine, then it has an outer electron shell that makes it stable, and chlorine has an outer electron shell that makes it stable as well. So that's all good and well. Now they're both stable, but by giving off an electron, you also give off a negative charge. So if you give off a negative charge, but you have the same number of negative charges in your electrons and to the same number of positive charges in your nucleus from the protons, which are positively charged, then that is usually in balance, right? In an element, that's usually in balance. Same number of protons as electrons. Well, if you give off or you take up electrons, then your charge changes. So sodium now is lacking an electron with respect to the number of protons, and so therefore it is positively charged, has 1 positive charge. And chlorine has picked up an electron, so it is now negatively charged by 1 extra charge, so it's 1 charge negative. And these types of completely stable and therefore completely either positive or negatively charged atoms are now called ions, because they are now charged particles. And so these charged particles are called ions. Okay, there's something really important about this. So if you are charged, if you can make an ion, then that means that the charge can allow you to change your properties, because charged things can interact with other charged molecules. We'll spend a lot more time about how that works and why that works. But in this example here, if you have sodium chloride, so a crystal of table salt, and you put that in water, so here's a tablespoon of salt in water. It's not yet dissolved, but you all know that it will dissolve, right? You can stir it up to speed it up a little bit. You can just wait and it will dissolve over time by itself. Up to a certain level, there is a saturation at what point it won't dissolve anymore. But let's not think about that at this point. Let's just think about how the dissolution occurs. And the way that it occurs is because these are all charged particles. So these charged particles that are positively charged, they can be dissolved because water, which is slightly charged because of its oxygen sort of taking on a little bit more closely to its nucleus, the electron from the hydrogen, are polar. So polar means they have two poles, just like the Earth, North and South Pole. They have a negative and a positive pole. We'll come back to that in just a second, why that is. But given that that is the case, there's a bit of polarity in a water molecule, a little bit of negative charge here, a little bit of positive charge here. They can mix very well with a positively charged ion. So you can see here, this will dissolve the sodium ion because it can now interact with the water molecules by orienting the water molecules such that the negative and the positive will interact with each other. Of course, the opposite is true for the chlorine or the chloride ion in this case, where we have a negative charge and where it can be dissolved or held in solution by these water molecules that are positively charged on one pole of the molecule. So let's go back to the water molecules and let's go back to the covalent bond. So if you have water molecules made up of hydrogen gas and oxygen producing water, these parts here are more negatively charged because oxygen has the ability to pull electrons a little bit closer to its center, but it can't completely take it away from hydrogen. So water never forms ions. And exactly what that property is that allows a substance to either completely take on an electron or just partially take it on, we'll come back to that in a moment. But you can see here that we have the positive charges and the negative partial charges. That's what this delta, this sign here, this Greek letter for D, delta, stands for. So we have a polar molecule, not an ionic molecule. There are covalent, it's a covalent bond in between them. And by the way, these molecules, as you're making a substance, are called reactants. They're reacting with each other. And then when they produce something, those are called products. Okay, so let's go back to the water. Let's go back to our two bonds that we're discussing right now. Hydrogen bonds are bonds that are a third type of bond, and they can arise in between two molecules of water because of the way that the molecule is oriented itself. So what do I mean with that? I mean that you see here that oxygen is slightly negatively charged on one end, slightly positive charged on the other end, but the next molecule over is also negatively and positively charged. You see here is the partial negative and the partial positive. They can align with each other. They can sort of orient themselves to each other so that they will interact. These two molecules now have attraction to each other. The positive and the negative attract each other. And so these kinds of bonds, they're very different from the covalent or the ionic bonds, much less strong. Those are called hydrogen bonds. And they're also very important, even though they're not as strong as the other bonds. In biology, they're very, very important. You'll hear about hydrogen bonds all the time. So we'll come back to those as well. So hydrogen bonds exist between partially negative and partially positive molecules. Okay, so when we talk about water, and we talk about these hydrogen bonds, one thing that's important, just sort of as an example, with water, using water as the example, the difference between liquid and frozen water, solid water, has to do with the hydrogen bonds and the energy that is between molecules. So if you have a substance and you heat it up, there's more energy contained in that substance. So think about a beaker of water, you add a little bit of heat, you put it on a heat plate, stir it up, it will contain more energy. And what that means really on the molecular level is that the molecules will start to swirl around a little faster. They can just move around faster. And that is because the energy from the heat will break the bonds that exist between the molecules. And so there are these molecules here that are not bonded, really hydrogen bonded with the next molecule. And so therefore the substance becomes a little bit less dense, the water is more likely to evaporate. And that, of course, is exactly what happens when you heat it up more and more and more. You see that water is starting to evaporate even before it starts to boil. And that is because water molecules are no longer interacting with each other, because the energy from the heat breaks these hydrogen bonds, takes them apart, and so eventually they can even evaporate out of the liquid phase. And in ice, of course, that's very different. There you have a crystal where every molecule is interacting with the next molecule over, and so that gives ice its specific properties. Okay, fourth type of bond. That's the van der Waals forces, and you see that they're called forces rather than bonds. And some people will argue those are really not bonds; they're forces. Well, I just list them here as the fourth type of bond, but let's call them forces, and then everybody's happy. So van der Waals forces exist between uncharged, usually long molecules. And the reason for that interaction that you see here through these little dashed lines is because even though they're uncharged, and we come back to what all these charges mean, where they come from in a second, even though they're uncharged, so for all intents and purposes right now, there's no plus and minuses here. There's also no delta plus and minuses here. They're just simply not charged. There is a little bit of an attraction between these two molecules, this molecule and that molecule, that you see here is made up of carbons and hydrogens. And each of these carbons is bound to another hydrogen or another carbon by sharing 2 electrons with each other, producing this bond. So these, in fact, are covalent bonds. But these bonds here, this, and that, they're not really defined exactly where they are. They're just sort of between this molecule and that molecule somewhere. Those forces are called van der Waals forces. And you will find them often in very long molecules. And fats, as we will talk about in the next lecture, have these types of molecules. And so therefore it's very important that we know what van der Waals forces are, because fats are very important for understanding biology. Okay, so 4 types of forces. We talked about covalent bonds, ionic bonds, hydrogen bonds, and the van der Waals forces. Now, to lift the cloud a little bit on understanding what really the difference between this is, I want to give you this rule of thumb. And that rule of thumb should make it much easier for you to understand, exactly what these bonds are. So let's go back to the periodic chart. And so this periodic chart is now color-coded in a completely different way than the first one. The first one was sort of functional for biological systems. This one is colored by a particular way of understanding these different elements. Each element has a specific property that's called the electronegativity. Very important for you to learn. It's bold and underlined. You should know what electronegativity is. And when you do know what electronegativity is, you understand a whole lot more about chemistry and biochemistry. So what is electronegativity? It's an element-specific property. That means you can't really change it. You can't calculate it. You can only look it up. That describes the element's ability to attract electrons to itself. Electronegativity. By what strength can this element pull electrons towards its center? That's what electronegativity means. The electronegativity value, or En value, allows the calculation of the type of bond this element will create with another element. So here we have it. In order to see whether you have an ionic bond or a covalent bond, you can use the electronegativity as a way to determine that. Here's the rule of thumb. If the electronegativity difference between 2 atoms that we're looking at to see whether they form an ionic or a polar bond, if that's greater than 1.8, an ionic bond will form. And if it's smaller, then a polar bond will form. Okay, let's look at these. If you blow this up on your screen at home, you can see the numbers as well. The numbers sometimes vary a little bit. That depends on who drew up this particular chart. They don't vary by much, and they don't vary in their reference to each other. But sometimes you will see, for example, for fluorine, it could be 4, it could be 4.1. Doesn't matter so much because it will always be the strongest electronegative element in the periodic chart. And you see that here by color shading. So the ones that have the highest amount of electronegativity is fluorine, chlorine, and oxygen. 4, 3.5, 3.5, or thereabouts. And then you have the lower ones. The further you go over to the left-hand side of the periodic table, the lower the electronegativity becomes. All of these guys have very low electronegativity. Now, we just talked about sodium and chlorine, right? We said that chlorine picks up an electron from the outermost shell from sodium and takes that electron into its valence shell, completing its valence shell, and leaving sodium with a complete outermost valence shell. And that, again, is because of electronegativity. So that one electron in the outermost shell in sodium can go over to chlorine because it has a much lower electronegativity. Chlorine will pull the electron. And you can calculate this value between 3.5 and I believe sodium is 1. That will be 2.5. And so therefore, that electronegativity difference between 3.5 and 1, right? 3.5 minus 1 is 2.5, is greater than 1.8. And therefore, there will be an ionic bond that is going to be formed between chlorine and sodium. So here's an example of how you can use the periodic chart with its electronegativity values to determine what types of bonds are formed. If we look at oxygen and water, right, oxygen and hydrogen to form water, 3.5 and 2.2, that difference is only, what is that? 3.5 minus 2.2, 1.3. So that is less than 1.8. Therefore, a polar bond will form. Having said that, there is a difference between electronegativity between these two, right? It's not big enough to form ions, but there is a difference, and that is what creates the polarity that we saw earlier here, for example, in this slide. See where I said this is slightly negative, this is slightly positive. Well, the reason for that is that, well, they're not ions, so it's not completely positive or negative, but they are slightly charged. And the reason for that is electronegativity, because oxygen has a higher electronegativity than hydrogen, pulling electrons towards its nucleus. So that is why you have the partial charges here between those two. Okay, so that's something you should definitely look at in the book. You should maybe Google it a little bit more. Just try to understand what electronegativity does and what it can tell you, because that's really the main explanation to all of these questions of when and where and why do we have polar particles forming and what types of polarity we get. Okay, so I want to finish up the lecture here by just showing you some ways of writing chemical formulas. You'll see those chemical formulas all over, and I want to make sure that you understand and appreciate what they mean and what we draw, how we draw it. You'll see more of that in chemistry as well if you take chemistry. So I mentioned earlier the chemical formula, the structural formula. So the structural formula tells you a little bit about the structure. How does this particular molecule look in a two-dimensional way to draw this on a piece of paper. And then the chemical formula, simply to save some space, it just gives you the sum of all of these atoms that are making up the compound. There's also a three-dimensional way to draw it, and that is when you use the molecular orbitals. And for carbon, it might be important to know that. I wouldn't say, well, it's probably important for all of them, but carbon is one of the most important elements, and so therefore in biology, and so therefore knowing the three-dimensional way, the shape with which it forms bonds is somewhat important. We'll talk a little bit more about that, but I just want to show you here the molecular orbitals. There's four. In the four corners of a tetrahedron, three-dimensionally speaking, is sort of like a pyramid, right? It's a pyramid with three sides, with 1, 2, 3 sides. So that thing, if you think about that three-dimensionally, no, it has 4 sides, right? It just has 4 corners, 1, 2, 3, 4 corners with a carbon in the center. So imagine that three-dimensionally, so that you can imagine that there are, how do we have this here? Like the 3 on the bottom and then the 1 on the top. So that would be the 4th, and then carbon is in the middle of it. Okay, so many ways to represent that. You can represent it in some sort of a 3-dimensional, 2-dimensional shape, structural, chemical formula, the sum formula. You can use the structural formula to show a little bit more about its shape. But you can also then take this shape. So this is an example of a sugar molecule. We'll talk about those later on as well. You see that this is sort of a 6-membered ring. And when you want to show the structure without writing down all the elements that are part of all the atoms from these elements that are making part of this structural formula here, there's also a simplified way to do that, and that is by just drawing the electrons. And the one thing that I want to make sure that you realize or appreciate, if you haven't before, that the structural chemical formulas are drawn by letters and lines, and the lines show the electrons, right? So these lines are the electrons that are making the bonds. So this is the bonds, 1 line, 2 electrons. Simple thing to remember. If you have double bonds, those are 4 electrons. And so that's what you need to remember when you see a structural formula, that these lines are indicating the electrons. Okay, so far so good. Ask questions next time in lecture if you have any. You probably do. So write down those questions on a piece of paper at the beginning of class. Ask me those questions. We can go over the slides again. Specific things that you want me to go over again, I'm always happy to do. Let me give you the summary of what we discussed so that you know what to focus on in your own way of summarizing your lecture here. So we discussed a number of terms. You should know the definitions of all of these terms here. I'm not going to reread them. Just take a look at them and try to start learning them. We discussed 4 types of chemical bonds. I stressed that those 4 bonds are important. We'll talk about them again. Here they are: covalent, ionic, hydrogen bonds, and then the van der Waals forces. And then we mentioned that the property of an element that determines what type of bonds are used is the electronegativity. So very important for you to know what electronegativity is. And we looked at various ways to depict chemical compounds in their structures. So all of those things you now have heard about. You can start internalizing. You can read that in chapter 2 in your book. And then we will discuss those in class a little bit. And then look at other things in ways how we can understand in what ways this is important for understanding how life works. And with that, I see you next time. See you later.